Welcome everyone. We just heard an excellent ITC colloquium by Brad Cenko, who used to be an undergraduate in the same place that he gave his talk today. He was less fearful of the comments today than he back then. We also have the honor of hosting George Efstathiou from the University of Cambridge in England, the real Cambridge in England. And he is the Sackler lecturer this afternoon. He will give the Sackler Prize lecture on the results from Planck. One comment about that I should mention is that George himself told me that he wrote every line of the code to analyze the power spectrum of the data from Planck. And that's why we should all trust the results. Even though the Planck collaboration is so big, you often wonder who is doing the work, and in this case it was George himself. George will talk a little bit later at lunch, and the same is true with Brad. So we will start with Raffaella Margutti, our own, and she will talk about the first search for SuperLuminous X-ray emission from SuperLuminous supernovae, and then we'll hear from George, who sent the title, "Is Avi Right?" I don't know what he's about to speak. The only thing I know is my wife asks this question every day. And if I were to invite her to give this talk, she would have a very clear answer. She would say sometimes. After George, we'll hear from Nia Imara, our own postdoc here. Joined us earlier this academic year, and is doing great work. And she will talk about rethinking a notable molecular cloud. And finally, we'll hear from Brad Cenko again, who will talk about the first discovery of a gamma-reversed afterglow independent of high energy trigger. And I guess there was a paper a few days ago on AstroPH just with this title. So go ahead, Brad.
Thank you, Avi. So today I'm going to tell you about one of my after-dinner projects. These kind of things that are a lot of fun, but also kind of risky, but potentially highly rewarding. So this is one of the three themes of my research. I attack the problem of who explodes, how they lose their mass, and what are the sources of energy that powers the stellar explosions. And in particular today, I'm going to tell you about my search, and my research tries to understand what is the source that powers superluminous supernovae. So up until a few years ago, this was a picture in the context of type 1 supernovae, so core-collapsed type 1 supernovae, so no hydrogen. And the most luminous supernovae known were those connected to gamma ray bursts. However, this picture changed a few years ago with the discovery of superluminous supernovae. They outshine ordinary supernovae and gamma ray burst supernovae as well by a factor of 10 to 100. And just to give you an idea of how much energy is there, for superluminous supernova, you can radiate 10 to 51 ergs. And the kinetic energy associated can be a factor of 10 higher, so 10 to 52 ergs. Naturally, the question that everybody has in his mind is, what is the source of energy that powers this exceptional emission? So this is the knowledge gap that I'm trying to fill up. And the way I'm trying to do it is by using late-time X-ray observations with XMM and SWIFT, and also late-time optical observations. I really hope to be able to add to this picture tundra in the future, because the angular resolution is really something that you need in this case. So what are the possibilities out there? What people started thinking about? There are basically three main scenarios you can think about. And the first is interaction. The second one, you have a lot of nickel. Third is you have a magnetar. So let me just go a little bit deeper in each of these three possibilities. So the first possibility is that you have your supernova, but your supernova happened to explode in a very polluted environment. So what happens is that your supernova shock starts to interact with these shells of materials that your progenitor ejected in the previous years. And thanks to this process, you're basically way more efficient in converting your kinetic energy into radiation. This model has a very nice prediction that a student of Avi, Tony, and Avi put out a couple of years ago. And the prediction is that you should expect to see very luminous X-rays. And I want you to focus on the fact that these X-rays are coming at late times, where late time for me means 100 days, and they can be extremely, extremely luminous. The other possibility that people thought was like, okay, these supernovae are just like ordinary supernovae, they just have more fuel than average. So here you have supernova 87A, so 0.1 solar masses of nickel, and here is a superluminous supernova. All you have to do is just to add a little bit of more nickel. Well, a little bit means 4 to 7 solar masses of nickel. But basically, the source of energy is just like that for an ordinary supernova, you just have more. Third possibility, oh yeah, and also in this model, you have a very nice prediction about your decay because you are powered by the radioactive decay of nickel-56. So you have this nice prediction of what you should see in the optical at very late times. Third possibility is that you have an extra energy source. You have a magnetar inside. Let me go here. You have a magnetar that is powering your emission. So what happens in this case is that you have an ionizing source inside your ejecta. And if you wait a little bit, the ionizing front is able to break out. And that is also a source of very luminous X-ray emission. And again, have a look at the time scales. It's around 100 days or even later. And it can be as bright as 10 to the 44 and even brighter, even more luminous X-ray emission. So basically, here are the three possibilities. You can either be more efficient than average, having more ordinary fuel, or have something extra. Those are the three possibilities out there. Okay, so the way you can test these three scenarios is using late-time X-rays and optical observations. And the interaction scenario has been invoked a number of times by people, essentially to explain type 2 supernovae, those where you have a lot of hydrogen around. In the case of nickel-powered supernovae, sometimes what happens is that the amount of nickel that you have to have there is larger than the ejecta mass of a supernova, which is actually a nonsense. It's a little bit of a problem. So what happened is that people really focused on this third possibility of magnetars. And here is just a gallery of number of papers that came out. People have been really pushing on this magnetar model, and all you're seeing here is the fit of the optical light curve with this model. But as you remember, this model also predicts very bright X-ray emission. So one way to understand if these people are right or not is to check if there is this associated very luminous X-ray emission. So this is the situation that was before the start of our campaign, and those are all the limits that were there 3 years ago, let's say that. And guess where the superluminous X-ray emission should lie? Exactly in the gap. So we decided, okay, we have this problem. We need to cover this part of the parameter space, and this is exactly what we did. More to the point, the only time when people went there, they found evidence for luminous X-ray emission associated to this transient, which is a superluminous supernova. However, this led to a very disputed claim of superluminous X-ray emission, basically because this first data point comes from an XMM detection, and the PSF of XMM is kind of large. And the second data point is Chandra. So all we can say right now is that for this particular transient, there was an X-ray source that was coincident as a position, and that this thing faded away. But since we have this just little amount of information, we cannot really say if that thing is really connected to the supernova or not. So it would be nice to be able to repeat the experiment and find others. And again, just I want to draw your attention to the luminosity of this transient and time scale. Just to put this thing into context and to make you realize how luminous is this X-ray emission from this transient, I draw here the X-ray emission from gamma ray bursts. all you can say is that SCP is actually way more luminous than even a gamma ray burst at this time. Okay, so here is the window that we decided we wanted to cover, and we've been awarded Swift time. We did it, and we started following up every single superluminous supernova that was close enough to do this kind of job. And here is the result. No detection. Okay. So let's just focus a little bit more on the magnetar model. I plotted here with these thick lines, the typical magnetar X-ray emission that you would expect. And as you can see, those 4 superluminous supernovae start to challenge this model. So we start to have an idea that superluminous X-ray emission is not for every superluminous supernova. It's not that we were just not looking there. Now that we're looking there, we don't find it. More to this point, we have been awarded an XMM campaign to follow up a Panzer object, PS114BJ. And as you can see, those are the first 2 limits, and there's going to be other coming up soon. All you can say is that the predictions of the magnetar models start to really get into troubles. And finally, more to this point, there has been a very recent superluminous supernova, PS115AE, and we have an XMN campaign that we hope to be able to match with Chandra in case of detection, and those are the limits that we will be able to put to this magnetar scenario. So the takeaway point that I want to take home from this talk is that it's not true that we were just missing, we were not sampling the phase space for superluminous supernova. What seems to be happening is that superluminous supernova X-ray emission seems to be something very rare. So at some point, this is going to be challenging for this model, which also means that maybe we should start thinking more about other possibilities like the interaction model as well. And for those who remember my talk last year, I just want to update the number of photons per paper with another point this year. So I'm still doing pretty well, following the Harvard trend, but it's always a matter of perspective. So my science at Harvard is, science per photon in Harvard is really, really skyrocketing. So stay tuned, and more results are coming. So thank you.
How robust is that prediction?
Yeah, exactly. So you can actually
believe they can be really 100% confident.
No, they're not. And I've been speaking a lot with Brian Metzger, and there are a lot of assumptions that are going there. And there is, first of all, it's true that this model, the X-ray prediction here, it really depends on the ejecta mass that you have. So if you have a lot of ejecta, your ionization front is not able to break out at all. So you can die inside. That's one possibility to reconcile our very deep limits to the model. Other possibility is that this is for very, very fast spinning magnetars, 1 to 2 milliseconds. But actually, if you have something that is not born as fast, it's possible that your ionization breakout happens as much later epochs. That's another possibility, and a much lower luminosity. That is why I'm really arguing that we need to go as deep as we can on a baseline that is at least a couple of years. And this is what we're going to do. And the goal is to start really to challenge this kind of picture. Yeah, right. That's another. Yes. That's correct.
So for the source SCP-06F6, was there an X-ray upper limit prior to first detection?
Oh, good question. I actually don't know the answer. I should have a look at that.
Other questions?
So this same strategy, and especially with XMM plus potential Chandra, what kind of constraints can you put on the interaction model?
Oh, that's an extremely good question. So actually what I'm arguing here is that people have been kind of dismissing the interaction just because it's more difficult to have a... So this magnetar model is very easy to fit to the data. So that's the real reason why, one of the reasons why people are going there. But if you have a detection and you have a spectrum, that really helps you understanding if you are in this regime or this other regime. So in case of non-detection, it's way harder. But if you have only X-rays. However, if you're doing X-rays, UV, and optical, that really helps you because the interaction is also going to show up as emission lines in the optical and UV, and this is what we are doing as well.
The interaction model is sensitive to what the star did before the explosion.
Yeah.
What was the mass rate?
Yeah.
Very close to the time.
Yeah, and by the way, while we're doing this exercise, we find another supernova that is likely belonging to this category, and I hope to be able to tell you the story in 1 month or so.
Would radio observations be useful for testing the magnetron model?
So I thought hard about that. It doesn't seem that there is a clear prediction as in the X-rays, but we're working in that direction too as well. Yeah.
If there's interaction, you could imagine radio emission.
Yeah, when you have a lot of interaction, you have also to worry about free absorption. You can be free absorbed forever. Yeah.
No more questions.
Thank you.
Oh, right. Thank you very much. Thanks. Okay, well, look, as the title suggests, I think you should take this in the spirit of light entertainment. So is Avi right? And I said that I wasn't going to tell you what I was going to talk about. So now, I'm an extremely unhappy cosmologist. And I'm unhappy because I don't like infinities. And so here are 4 examples of where we have infinities in physics that I think that we should be deeply concerned about. One is that inflation, particularly with the constraints from Planck that I'll talk about in the Sackler lecture, inflation is eternal. Once inflation starts, it never ends. And so there's an infinite number of possibilities that can happen if we had inflation at any point in the universe's history. Now, another place that infinities arise is in string theory, which predicts large numbers of metastable vacua, and if these things, if there's any truth in that, then one metastable vacuum will be able to decay into another metastable vacuum, and so the entire landscape of metastable vacua will be populated and will exist, and predicting an infinite number of pockets of the universe. Then the third example comes from late time acceleration. If we have an infinite de Sitter future, then every point in space is surrounded by an empty cavity. It's not completely empty because it radiates, and then the thermal fluctuations will make things happen. And so that leads to the Boltzmann brain paradox, that consciousness, fleeting moments of consciousness, should dominate over other types of consciousness. And we are not Boltzmann brains. Though sometimes when I come to the US and I watch the fleeting moments of consciousness on Fox News, I wonder whether that's true. So there are infinities associated with the late time acceleration. And then there are infinities associated with quantum mechanics. And here I've put many worlds as a proxy for whatever your favorite interpretation of quantum mechanics is. And in many worlds, the infinite possibilities of an infinite Hilbert space actually exist. And some people have tried to relate these together. So, for example, you will find papers in which people try and interpret quantum mechanics in terms of, real representation in the multiverse. And, you can understand the Born rules of quantum mechanics in terms of frequentist statistics within the multiverse. Okay, so there are these examples of infinities, and most of us have day jobs where we have to do serious science, so we don't think about these things, unless you're from Stanford, in which case this can be your day job. And the reason that we don't talk about it is because we don't really have anything particularly sensible that we can say about them. Okay? These infinities, these are not problems that are going to be solved by some application of high school math to find a new measure on the global structure of the multiverse. What they're telling us about is that there's something very deep within physics that we don't understand. That's potentially holographic or something complicated. So there are an infinite number of infinities, and cosmology is an absolute mess. And it's a mess that, puts the problems of classical physics, the turn of the 19th century, these dwarf those problems. And I think it's going to take a similar revolution in our understanding of physics to understand these issues. So, although if you come to the talk this afternoon, I will present a great case of how much we've learnt about cosmology. We have these problems that tell us that cosmology is an absolute mess. Okay, and that's basically the message that I want to send from the real Cambridge. Cosmology is an absolute mess. Now, how does this fit in with Avi? Well, he's... he has co-authored 2 papers, okay, both making the case that inflation is a mess following the Planck results. So I'm not going to go into detail with all of the arguments that they present in the papers, but I'll just give you a flavour of the sort of argument. Here's an inflationary potential which has a flat region here and then a steep region over here. Now, the Planck data say that the potential of inflation has to be flat. So in this schematic picture, that you have to go through an inflationary phase on this part of the potential. But if the field were up here, you can also go through an inflationary phase. But if you put the field up here, you're rewarded with exponentially larger volumes than you are down here. So it doesn't seem natural to say that we start here. You're exponentially rewarded in volume if you start up there. So there's a problem with initial conditions. And if you start up here, then generically you'd expect a small shift in the spectral index from a scaling variance spectrum that's of order 1 over the number of e-folds, and there should be an associated gravitational wave component with a tensor to scalar ratio that's also of order 1 over the number of e-folds. And we're pushing on this boundary now. Okay? That is the reason why we infer that potentials are flat. So there needs to be some sort of fine-tuning here. Okay? That's basically the argument. But we can imagine other possibilities. So here I've just listed a few examples. If inflation is realized in an unusual geometry, for example, by branes moving inside a warped geometry, then there are geometrical constraints in this type of model. The distance between the branes, brain to the tip of this region, this distance is, in effective field theory terms, the inflaton. Okay? And there are geometrical constraints that bound the change in the inflaton to be much smaller than a Planck mass. And in this type of model, inflation ends abruptly when branes collide, and so you've got a hybrid-like end, sudden end to inflation. In this type of model, the potential can be whatever it is that you want it to be, depending on the structure of the theory, and the tensor to scalar ratio can be very small. So maybe that's and I mean, by very small, John will never discover them, okay? So the potential could be flat, and it's just, you know, a question of the allowed geometries from a higher dimensional UV complete theory, okay? Another possibility for a flat potential is that there's a shift symmetry that we don't understand. We haven't understood the origin of this shift symmetry, but the inflationary potential reflects, the flatness of the inflationary potential reflects this shift symmetry. Another possibility is that we have an interaction between an inflaton, a light inflaton, and some heavy field. And so we can easily make a toy model. This has been looked at by Silverstein and collaborators at Stanford. So here there's a coupling between the light inflaton and a very heavy field. And the heavy field will then relax to produce the minimum in the potential. And that relaxation means that the effective potential for the light scalar field can be flattened. You see, in this simple example, if this term dominates over this term, then we get an exactly flat potential. Okay, so that's another possibility for producing a flat potential. Or we could imagine that we have a transition within a string landscape from one vacuum state to another, and we, you know, make a transition to a steep part of the potential, and that the potential just looks like this, and we roll down a flat region. So, so there are many possibilities. You know, this is all physics that we don't really understand. So, is Avi right? So the bell has come at just the right time. Do you want to know the answer? You do. Okay. Well, is Avi right? The answer is yes. Right? Inflation is an incomplete theory. We don't understand the initial conditions. There are problems with measures within a multiverse, and we need to understand all of these infinities. And I think we'll need to resolve the problem with all of these infinities to really understand how inflation works. But that's not the full answer to my question. The second part is no. This does not mean that inflation is in trouble. Okay? It just means that there are many open problems in cosmology. I mean, there is no example that I know of in theoretical physics where you insist that the theory explain its initial conditions. Okay? So I don't think that the fact that we have these problems is a problem for inflation. But the problems that Avi and colleagues raise are important problems. They're really they're a reflection of this fact that cosmology is in an absolute mess. And we often talk very tritely about inflation and say things like inflation predicts that the universe should be spatially flat, and we really don't know that. Okay? And so we should just acknowledge our limitations of what we do understand when we teach inflation, when we talk about inflation. So I think that Avi's wife will be very pleased at the result to the question, because is Avi right? Well, yes and no. Thank you. Right.
Because we know the history of every cycle of the
Yes.
solar system, right?
Yes.
So what is your taste in terms of how many free parameters should be introduced? Because any new data point we can introduce
Okay, so I certainly agree with the first part. I mean, you know, this is my complaint about, you know, what I'm saying here when we teach inflation. Inflationary models certainly have attractor solutions, okay? But that doesn't mean that you're free of initial conditions, okay? And these infinities, you know, they're, you know, I mean, we can overwhelm the predictions of a spatially flat universe by choosing different measure, okay? That's the point that you make in your papers, and I agree with that. So it's clear that inflation is a deeper theory. It's not divorced from initial conditions, and it's not divorced from these measure problems, okay? So now I've forgotten the second part of your... Oh, and how many free parameters? Well, I don't care. Yeah. Right, okay. And on that, I don't care. I think we should be empirically driven, okay, and not worry too much about what, you know, how many parameters we need to describe the inflationary potential. I mean, that depends on the actual inflationary models. For example, here, I mean, you know, it's subjective to say what is natural when we don't understand the physics. To some people, this kind of model might seem natural. Inflation ends abruptly here. If you try and describe it, you know, in terms of a single field model, it looks like a really finely tuned model, okay? But it has a geometric interpretation, which to some people may seem more natural. So I'm not worried about, you know, I think arguments based on a simple polynomial-like potential, how many parameters do I need to describe inflation, I think those are too simplistic. So I don't give them very much weight.
George, I've heard of Boltzmann's H theorem, right? And in fact, I've heard it said that Boltzmann could face all the paradoxes that came from the H theorem, and that's why he committed suicide. But I've never heard of Boltzmann's conscious brain. So I was wondering if you could very briefly remind us or tell me. I've never heard this before.
Okay, so look. I mean, some people don't like talking about Boltzmann brains, you know, because it is so weird. But okay. I think it's a real problem. Let me phrase it in another way. If I have a finite thermodynamic system, then you know that you can get recurrences, and you know, unusual things can happen. So and the reason that so we could get a fluctuation that could reproduce something like the Big Bang, okay? But if it were a recurrence, it would be exponentially more likely that when we look back in the history of the universe that we'd have seen some chaotic state that was not in thermal equilibrium. We don't see that. We see it's thermal equilibrium all the way down as far as we can see. And so that's why I say with real confidence that you know, we are not Boltzmann brains. Okay, so therefore, infinite de Sitter future doesn't make any sense.
Still missing the brain part.
You don't have to worry about brains, okay? You just have to worry about, you know, the fact that our universe is...
Surrounded by vacuum, just thinking about it, isolated brain in an empty universe, which is much more likely to be the case if you think about the Sitter space for infinite amount of time.
Yeah.
So if you extrapolate to the future, we're much more likely to exist in the future.
But I do like to think of it in terms of this fact that when we go back in time, the universe it looks in thermal equilibrium. That is really unlikely, right, from a Boltzmann brain perspective, right? So we are not Boltzmann brains, I think. My take is that these infinities don't exist. Okay, so that this is a problem that we have in our understanding. That's why I sort of hinted at a sort of holographic interpretation. Okay, so I think parts of the universe may be mirrored onto other parts of the universe through some sort of holographic type idea.
Everything that can happen will happen in infinite number of times.
Yeah. Well, look. This is wild speculation, but so. instead of the same thing happening an infinite number of times, that same thing is identified. And so there's a non-locality in physics that we don't understand. And that's how you regularize the infinities. Now, please don't repeat that to anybody outside this room, okay? It's just completely wild speculation. Twice the, you know.
Every human is going to be born at some point.
Yeah.
Will be born. We're likely to be somewhere in the middle. So calculate the growth of the
It's
population.
2t.
Time, and we're about in the middle, and population is growing exponentially, so the future is like one generation.
Yeah.
So that's the future of humanity. But obviously this has like, without knowing the fires, this is kind of a useless statement. Right? Because in 1,000 years, there's so many humans that are going to think that the expansion is one generation away.
I mean, Jerry Oestreicher is, you know, he's easily excited, okay? But I once made him incandescent with rage when I said that I thought the most famous person to come out of Peyton Hall would be Richard Gott because of his doomsday argument, and that led to a Jerry explosion. Oh, yeah, sorry.
Okay, left it. I'm going to give that back to you. Yeah.
All right. Good afternoon, everybody. My name is Imara. And today I'll present an overview of some of my recent findings regarding a giant molecular cloud that is unusual in the sense that it has very little star formation compared to other molecular clouds we know of in our galaxy. Giant molecular clouds are important to us because as the main reservoirs of molecular gas in the Milky Way and other galaxies, they have a bearing on galactic evolution. And since all stars, at least in the local universe, are formed in molecular clouds, an important goal of star formation theory is to explain how these entities form and evolve. So clouds in different environments or with unusual properties may represent different stages of cloud evolution and should be studied in order to form a comprehensive view of star formation. This year is actually the 30-year anniversary of the discovery of the cloud I want to tell you about. The Madalena molecular cloud, also known as G216 2.5, is located 2.2 kiloparsecs away in Monteceros. It was first discovered as part of a galactic CO survey with what was the 1.2-meter Columbia telescope and is now the 1.2-meter telescope here at the CFA. And I've also highlighted the Rosette molecular cloud, which I'll be talking about more later on. So what you're looking at here is the CO 2.6 millimeter emission of Madalena for those of you who aren't radio astronomers. CO lines are what we typically use to observe GMCs and measure their properties, since molecular hydrogen, the most abundant molecule in GMCs and in the universe, can't be seen in emission at the cold temperatures of molecular clouds. And at more than 100,000 solar masses and about 100 parsecs across, Madalena is one of the most massive, largest, and lowest luminosity nearby clouds. But whereas most clouds in the galaxy are actively forming stars and host at least one massive star, Madalena appeared to be devoid of any star formation when it was first discovered. In the 90s, Lee et al. Used IRAS to identify possible sites of low-level star formation at the periphery of the cloud and in a satellite cloud. And only a few years ago with Spitzer did Megeith et al. Find concrete evidence for a small amount of star formation occurring in the main body of the cloud. Now, the fact that molecular clouds have different levels of star formation activity is not new. The fact that this activity seems to be independent of cloud mass isn't new either. But what makes Madalena interesting and seemingly unique is that it has an extremely low star formation efficiency, and also that it doesn't host any high mass stars. So all in all, the evolutionary status of this GMC has been somewhat of a mystery. It's been debated that it could either be a very young cloud or else an old relic that had a higher star formation rate in the past. So in light of new observations of this and other clouds since Herschel, and given new developments in star formation theory, I wanted to take another look at Madalena. For one, I considered the X factor, a ratio that astronomers have used for years to convert the intensity of optically thick CO emission to an H2 column density. Now, although this is a simple idea, when we use the X factor, we have to be mindful of all of the physics that are subsumed into this coefficient. Environmental factors including metallicity, radiation field strength, excitation, cloud morphology, and dynamics all are expected to influence X. And yet, for several decades, it's been known that this conversion factor, which has been determined empirically using independent methods, takes on roughly the same value for clouds in the solar neighborhood. Nevertheless, as we explore the properties of GMCs in the outer galaxy and beyond the galaxy, there's continued interest in X, both from observational and theoretical points of view. So I wanted to know if on small scales, X and Madalena might depend on local cloud conditions, as is predicted by theoretical studies of the photodissociation regions around clouds. This plot by Bell et al., for instance, shows that the X factor changes with optical depth and with average cloud density. Their models predict that at first X drops from high values to a minimum between about 1 and 3 AV. And the high values of X up here arise because CO hasn't yet become optically thick, and X is inversely proportional to the CO intensity. But after the line becomes optically thick, X rises again with increasing extinction, which is equivalent to the cloud column density. Now, as the overall volume density of clouds increase, the CO molecule is shielded more efficiently, and the minimum value of X goes down because the molecule is more abundant. And most GMCs have a number density of about a few hundred particles per cubic centimeter, but Madalena has about 20 to 50 particles per cubic centimeter, so you might expect it to have a higher X factor based on models like these. So using far infrared data from Herschel, I modeled the dust emission in Madalena to construct a column density map of the molecular gas, which you see in red. And I compared this map on a pixel by pixel basis to the CO emission shown in contours. And the resulting X factor map looks like this. And so it shows that X is lowest in regions where we have signs of star formation. It's quite high in some unexpected places, like here and over here. And part of my ongoing work is trying to figure out what's going on with the gas kinematics in subregions of the cloud. Now, globally, the mean value of X in Madalena is very close to X in the solar neighborhood, which was somewhat of a surprise. I also derived the X factor for the Rosette, an evolved cloud with a much higher star formation rate and a lower mass, and found that it takes on a slightly larger value than Madalena, but within the error bars they're consistent. And so, changing topics a little bit, in the star formation community, there's quite a bit of interest in the distribution of gas in molecular clouds, the probability distribution function. And my work shows that this is actually using the same Herschel data, that Madalena has a PDF that is partially log normal with that ubiquitous power law tail at high column densities that we've seen in other galactic molecular clouds, and which theory interprets as being due to self-gravitating star-forming gas. Now, since much of the dispersion in the PDF and also the X factor might arise from region-to-region variations in the physical environment of the cloud, I wanted to ask the following question. If some regions of the cloud are more conducive to star formation than others, would the PDF tell you so? So I looked at different regions of the cloud. I compared regions that have signs of embedded star formation shown in the dashed circles, and I compared those to regions that, as of yet, haven't shown any sign of star formation activity. But before I show you the results, I wanted you to take a few seconds to guess which one of these subregions, based on the PDFs, is the star-forming one. And I know that we have at least a few PDF experts in the audience. I heard a C. Anybody else?
A and C.
There's just one star-forming region here. And we have one B. All right. Well, that's good. You guys have helped to prove my point. It's actually region 1. And, I'm sorry, region A, or letter A, region 1. And these are the results for all 9 regions on the same scale. So I found that the PDFs of star-forming regions do appear to have power law tails, although they're not all quite so dramatic. And it's also really interesting that the widths of the PDFs vary between star-forming regions. And that width, theory predicts to be correlated with the sonic Mach number of the gas. They're not uniform. Also intriguingly, like you saw in the last slide, some of the regions without signs of star formation show indications of power law tails, and they peak at higher values than the global mean, indicated by the dotted line. So at least 2 morals of this story. A, we have to be careful when we interpret the column density PDF, since high column density gas may not always correspond to high volume density gas. And B, we have to, or perhaps what we're seeing in some of these non-star forming regions is signs of incipient star formation. So I also compared the global PDFs of Madalena and the Rosette. But I think this plot is a bit more telling, at least in an immediate way, the plot of their cumulative mass functions. It shows in a really striking way how over a wide range of column densities, the Rosette has a higher fraction of its mass locked up in dense gas than does Madalena, which really brings us to the point. The key to understanding different star formation rates is addressing the question, how is dense gas produced, and what explains variations between clouds? As far as I know, there's not a complete answer to this question yet, but I want to prove to you in the last few slides that this is the question we should be asking. Observationally, we know that stars form in cores having densities in excess of the average molecular cloud density by at least 2 orders of magnitude. And based on observations of high-density tracers like HCN and ammonia that require high H2 densities to be observed, Lada et al. And others argue that this high-volume density material corresponds to high column densities of extinction, or extinction of at least 7.3 magnitudes. So the star formation rate might be expected to correlate with the total amount of dense gas above this threshold. And indeed, although Madalena is the more massive cloud overall, only a small portion of that mass is in the form of dense gas capable of producing stars, which is sort of to be expected, but now it's quantified in a nice way. Only 874 solar masses in Madalena is above this threshold, where nearly 1,400 solar masses, or 4% of the Rosette's mass, is above this threshold. And so, as you saw on one of the earlier slides, while there's not a strong trend between star formation rates and GMC mass, Lada et al. And others show that there's a good correlation between the star formation rate and the amount of gas above a certain extinction or column density threshold. This fit to the data amounts to a prediction that the star formation rate scales with the amount of dense gas above the threshold. And when you consider the amount of dense gas and the number of protostars in the Maddalena cloud and the rosette, it turns out that they follow this trend pretty well. So to summarize, while Maddalena has a greater mass than, let's say, an Orion or a California molecular cloud, it has a star formation rate about half of Taurus or Ophiuchus, which might be familiar to you. So as I move forward, one of the things I'll be looking more into is the nature of the dense gas in Maddalena, with the goal of understanding how molecular clouds in general evolve to become star-forming. I'll leave you with my conclusions. The CO to H2 conversion factor in Maddalena is about the same as other clouds. The PDF of Maddalena is log normal with a power law tail, but in addition, it has a significant low density component to it. There are regional variations which don't seem to be all explained by whether or not the regions are star forming, and the rosette has a higher fraction of dense gas than Maddalena. And not so much of a conclusion, but a future goal is to understand better how dense gas is produced. Thank you. I would say so, yeah. The shapes definitely of these clouds are very complicated, and it's just one thing among others that you have to consider.
Do you have any information on magnetic field in Maddalena? Is it peculiar in any way?
Actually, I don't. I don't think that it exists. Even though it's been known about for about 30 years, it's largely unexplored territory as far as observations go.
Do you have the information on the Mach number in the cloud?
My calculations say that it's about 40 or above. It actually, I didn't go into the kinematics much, but it actually has a pretty broad line width that's comparable to other clouds. Mm-hmm.
Oh, yeah, really quick, just in terms of the regional variation, so the box size, you calculate the PDF over, the regional variations will change dramatically with different box sizes.
I account for that. It's actually pretty robust, and I made sure that I had a certain threshold of pixels in each region.
You should talk to Hope then, because he's been playing with that exact same thing. He's
Right.
got a big variation.
Okay. Thanks.
All right, thank you. I have to say I was really intrigued by the title of George's talk. It sounded much more interesting than mine. So I thought, how would I try to answer this question? Thinking about brains and multiverses, doing real math and physics makes my head hurt. So I did what I usually do for my research, and I looked for the answer on Wikipedia. And if you actually go through and read this, it's pretty clear that the answer is a resounding yes to is Avi right. So what I actually want to tell you about today is a sort of a cute story, a paper that came out on Sunday night on the archive. In our basic picture of long-duration gamma-ray bursts, we start with a massive star progenitor, undergoes core collapse. For some reason we don't particularly well understand, it generates this narrowly collimated ultra-relativistic outflow, this jet. Some kind of dissipation within the outflow, whether it's internal shocks, magnetic fields, gives rise to this short-lived, high-energy radiation we call a gamma-ray burst. Eventually, this jet is going to sweep up whatever is surrounding that massive star, in part injects energy into the circumburst medium, accelerates electrons. You get this broadband synchrotron radiation and the optical X-ray radio wavelengths that we know of as the Afterglow. So this picture has been around for a pretty long time, and pretty early on, actually, it was realized that if these events are narrowly beamed, with opening angles of, let's say, 1 to 10 degrees, there should be on the order of 10 to 100 of objects for which we actually don't see the gamma ray emission, but it's because it's beamed in some other direction, but it's actually still possible to detect the afterglow. We call these orphan afterglows. The reason for this is because of relativistic effects. Initially, the radiation is beamed into a very narrow jet. Eventually, when the Lorentz factor slows down to about 1 over the opening angle, you see this sort of lateral spreading of the jet. And eventually, the afterglow is going to illuminate a larger and larger fraction of the sky. And even if you're sitting here off axis and miss this early emission, you'll see this sort of late emission. So these are theoretical predictions for what afterglow emission in the optical might look like. If you're looking sort of on axis, you see this rapidly fading emission. But as you go to wider and wider angles off axis, you see sort of rising emission that adjoins what you would see if you were looking right down the jet. There have been a number of attempts to try to find these kind of orphan afterglows, including by a lot of people here. One particular tack to take for this is to look at nearby core collapse supernovae for evidence of bright radio emission that you might see at late times. This is from a relatively recent paper by Raffaella. If you look at how the energy is partitioned by different kinds of massive star explosions, in general, the amount that's coming out with pretty slow speeds, ejective velocity that are, 10,000 kilometers a second, something like that, is reasonably well clustered. Most core collapse supernovae couple very little amount of energy to fast-moving material. Gamma ray bursts are the exception, where they actually couple a comparable amount of energy to this sort of very fast, let's say Lorentz factor of 10 or higher material. And this is why we say they're powered by some kind of central engine that's really driving this outflow. And more recently, there's been a class of sub-energetic gamma ray bursts, relativistic supernova, that seem to sort of span this bridge. So the radio world has shown this kind of very diverse picture of massive star explosions, where we see very different amounts of energies coupled to the fastest moving ejecta. The approach that we've taken, instead of looking at the radio, is to look in the optical. And just about a year ago, we made sort of our most relevant discovery here. These are discovery images of the transient source IPTF, or Intermediate Palomar Transient Factory, 14YB. On the left here, you can see this is a reference image taken sometime in 2012 and 2013. It's much deeper because it's a stack of many images. We obtained our first 60-second R-band image at about 9 o'clock UT on the 26th of February. There was nothing at this location. We come back about an hour later. There's a bright source, 18th magnitude. Come back a few hours later, and that source has faded significantly by about a magnitude and a half. So this kind of rapid variability is pretty uncommon. You certainly never see this in supernovae. You do see it occasionally in flare stars, but I'll show you that that's not what's going on here. What I want to highlight here is sort of the time scale on which all of this science is happening. So we have our non-detection at 9 o'clock. We have our first detection at 10, second detection 2 hours later, and then our software is picking that up, within an hour of discovery. We're realizing that this is something pretty interesting, getting Keck spectra just a couple hours later, and actually getting, prompt satellite response from something that's orbiting the Earth, again, all within 5 hours. So this is really fast stuff happening on, I think, pretty impressive timescales. And there's a tremendous amount of manpower effort in terms of software development that has gone into making this kind of stuff possible. When we got the spectrum, we were extremely excited because you can see there are clearly absorption lines from a variety of different features, all at a redshift of about 2 that firmly establish this is something at a cosmological distance. The implied luminosity is tremendous, like minus 27 absolute magnitude in R band, And so this is something that looks exactly like, GRB-like relativistic outflow. And the first time that we were actually able to detect it independent of any kind of high energy gamma ray trigger. Now, unfortunately, our enthusiasm was slightly dampened later on. At the time, we have like a 1 hour window, right, where the GRB could have been going off. Right within that window, the interplanetary network of high energy detectors looked at their data. They take some time to actually get their triggers because their satellites are actually pretty far away from the Earth. You have to do some correlation to find these things. And right in the time window, that 1 hour time window, consistent with that location on the sky, they found this sort of bright flash of gamma rays. So you can go back and do probabilistic arguments and say that almost, with a very high degree of certainty, this is a normal, on-axis gamma ray burst afterglow, just like all the ones that Swift and Fermi find. It was just identified in a slightly different way than every other one before has been discovered. So even though we were a little disappointed, we were looking for these kind of orphan afterglows, we can still say some interesting things about the rates of things that look like this. There have been predictions that maybe there should be relativistic explosions where, because of some kind of mass loading within the jet, you don't see any gamma ray emission. These are the limits that we get in terms of a volumetric rate. Not surprisingly, with one event, it's pretty large error bars, but it's clear that when you compare with the rate of gamma ray bursts that are on axis, you pointed along our line of sight, that it's not like there's this huge population of events sticking up here. It's consistent with the on-axis gamma ray burst rate. You can also see that when you compare with other surveys that are looking at sort of even shorter time scales, this is like the first time we've actually been able to drive the limits down to sort of interesting levels. Prospects for doing more of this in the future. We're currently working on building a new camera for the 48-inch telescope at Palomar, which is where a lot of this work was done. The name of the facility when this camera is installed, the Zwicky Transient Facility. The idea is to populate essentially the entire focal plane of the Schmidt telescope with CCDs. So instead of looking at 7 square degrees, you can look at about 45 square degrees. These circles are for vignetting. So the outer field of view will not quite be as sensitive. This is, I think, 10%, 20%, 30% vignetted. But when you combine the fact that you're seeing a factor of 7 larger in field of view, and the new electronics installed will allow you to read out the detector much faster, you can actually increase your survey volume by more than an order of magnitude. So we expect when we're getting down to these kinds of aerial coverages that we should be able to see several orphan afterglows per year, and hopefully for the first time really be able to say something meaningful about what the from orphan afterglow detections, about the collimation of these events. So that's it. Thank you.
So if most afterglows are expected to be orphan, is it not very interesting that the first one that we find is not orphan?
Yeah, so you can try and back out from the fact that people have made a variety of predictions for, as a function of, let's say, optical magnitude, how many off-axis events you should see compared to how many on-axis events you should see. Those range from a few at the magnitude levels that PTF is looking at down to, less than 1. And it depends on what you assume for the typical collimation of these events and what you assume for how they sort of spread laterally, what their off-axis emission looks like. There's sufficient amount of uncertainty in those models that we can't really say GRBs must be this much collimated from what we have right now, but we're definitely pushing in that direction.
So the Grinnell models that you showed seem to be kind of a smooth continuum in angle. Does this maybe suggest that if you're on axis, you see the afterglow really well, and if you're very slightly off, maybe you see a much reduced value? It's not a smooth transition, maybe a
It's certainly possible. There have been many more updated models since then. I mean, it's hard to infer jet structure from what we have right now. But it definitely, you know, you could imagine, right, the most common viewpoints are the ones that are sort of just off axis, right, which is what I think you're getting at. And so the fact that we don't see lots of just off axis things means that they're probably not there. It's plausible, but I don't think we can say for sure yet, given the uncertainty in these models.